Okay, exercise 907 is conditional probability. I will apologise a bit in advance, this is quite a long one. We're going to start with a small review of the product rule for independent events. So remember, we found that the probability of A intersection B for independent events is just multiplying those. So for example, the probability of getting a head and an even number when rolling a coin and a die. So those are independent events because what you get on the coin doesn't affect what you get on the die and vice versa. So event A is getting heads and there's a 50-50 chance of getting heads. Event B is an even number on a die, which again is a 50-50 chance, so that's also half. So the probability of getting heads and even, you just multiply them. Half times half, which equals 1/4. Okay, we saw that in a previous exercise. Another thing we saw in a previous exercise was the addition rule of probability, which is the probability of the union of two events. You add them and you subtract the intersection. So let's have a look at what I mean. This is an example. So event A and event B in this Venn diagram. So the number in the whole sample space is 8 plus 2 plus 5 plus 5, which is 20. The number in A is 10, the number in B is 7, the number in the intersection, remember, is that 2 in the middle, and the number in the union is the 8 plus the 2 plus the 5, which is 15. So the probability of A is the 10 out of the 20, okay, which is half. I'll write 10 out of 20 equals half. The probability of B is 7 out of the 20. And the probability of the intersection, right, we can look here, is the 2 out of the 20 or 1 on 10. The probability of the union is 15 out of 20. If I divide by 5, that's 3 out of 4. Now let's have a look to check this rule here. So the union is P of A plus P of B minus the intersection. So basically that's saying all of A, which is the 8 plus 2, plus all of the B, which is the 5 plus the 2. We've double counted the 2, so we have to subtract off the 2. Okay, so let's just check it. So P of A was half, P of B was 7 on 20, minus the intersection, which is 1 on 10. And if I work that all out, I do indeed get 3/4. Okay, so I'd just like to give a definition and a formula for conditional probability. So a notation is this, which is read the probability of A given B, which basically means the probability that A happens given B has already happened. And the formula we get is that it is the probability of the intersection of A and B divided by the probability of B. Okay, this one matches with that one. And one thing you will get here is the sample space is reduced. Our sample space is actually B, not all of what we were doing. So I'm going to use that example to show you exactly what I mean. So the probability of A given B is basically the probability of A out of the B. Okay, so remember, this was our A, this was our B. So we're just looking out of those 7. So it's these 2 out of those 7, because those 2 are also in A. So probability that A happens, given that they are in B, is the number in the intersection divided by the number in B. Now that's not exactly what I had written on the previous page. I had probability there, which I'll just show you where that comes from. Essentially what I'm going to do is divide the top by the number in the sample space and the bottom. Okay, so this becomes N in A intersection B over N in sample space over N in B over N in the sample space. Now this is the probability of the intersection. How many are in the intersection out of how many in the whole sample space? So that's the probability of A intersection B. And then this one is the probability of B. How many are in B out of how many are in the whole sample space? So that's the probability of B. So that's that formula we just saw on the previous page. Also, if I just compare this and I multiply both sides by P of B, we can say the intersection is equal to the probability of B multiplied by the probability of A given B. We can also consider the case of independent events. So we know that the probability of A given B is the probability of A intersection B over the probability of B. But when we have independent events, remember we just saw in our review that that's just the two multiplied together. So that's P of A times P of B over P of B, and the P of B cancels out. So it just equals P of A. Now, if I switched all the A's and the B's here, I would also get the probability of B given A equals just the probability of B. So if all three of those probabilities or four of those probabilities are equal to each other, we know we do have independent events. So going back in this example, the probability of A given B is the 2 out of the 7. The probability of B given A is these 2 out of this 10. So 2 out of 10, or 1 on 5. And notice they're not equal, and they're not equal to the probability of A. The probability of A is 10 out of 20, as we saw on the previous page, which is half, which is not equal to this. Okay, so these are not independent events. So let's look at an example using a two-way table. So data was collected on the languages studied by a group of students as follows. So here we go. Students that study French and Italian, there are 15. French but not Italian, there are 48. Not French but yes Italian is 32. Not French, not Italian, there were 25 of them. And I've totaled each of those. So it says find the probability that a student studies French given they study Italian. So what we're looking at here is out of all the students who study Italian, there are 47 students who study Italian, and the probability they study French would be that 15 out of that 47. So I'm just keeping this really simple. The probability that they study French given they study Italian is the 15 out of the 47. So the probability that they study Italian, given they don't study French. So the probability that they study Italian, given those that are not studying French. So we're just looking out of the ones that don't study French. So we're looking at this column here, and so it's the 32 out of the 57. 32 out of 57. Okay, example 2. In a school, the probability a student studies mathematics extension is 0.15. The probability a student studies English extension and mathematics extension is 0.02. What is the probability a student studies English extension given they study mathematics extension? So what we were told is the probability that they study mathematics extension equals 0.15. The probability they study English extension and mathematics extension is 0.02. And we're asked for the probability that a student studies English extension given they study mathematics extension. So that's the probability of English extension and mathematics extension out of the probability of mathematics extension, which equals 0.02 over 0.15, and that simplifies to 2 out of 15. Now I will just mention too actually that this formula is on the reference sheet. Okay, example 3. Now I'm going to do this one with a tree diagram and fill it in as I read the question. So this is about strawberry and vanilla ice cream, liking strawberry, not liking strawberry, liking vanilla, not liking vanilla. So the first sentence says the probability of liking vanilla ice cream when you like strawberry ice cream is 9 in 10. So you like strawberry, the chance you like vanilla is 9 out of 10, which means the chance you don't like vanilla must be 1 out of 10. because of course they have to add to 1. Then it says the probability of liking vanilla ice cream when you don't like strawberry ice cream is 3 in 10. So if you don't like strawberry, the chance of liking vanilla is 3 in 10. So this must be 7 in 10. What is the probability that you like strawberry given you like vanilla ice cream, given 50% of people like strawberry? So strawberry is a 50-50, so half and half on my tree diagram. Okay, so the probability of liking vanilla, well, that is this group and it's this group. So I need to multiply across and add down. I've got half times 9 on 10 plus half times 3 on 10, which is half times 12 on 10, which is 6 on 10, which obviously is 3/5. We'll just leave it as 6 on 10 for now. The intersection, remember, is and strawberry, probability that you like strawberry and you like vanilla. So that's just that top branch. So that's just half times 9 on 10, which is 9 on 20. So the probability that you like strawberry, given that you like vanilla, is the intersection divided by those who like vanilla. So that's 9 on 20 divided by 6 on 10. Okay, remember, keep the first one, change the middle one to it, and flip the second one. We could have done something else there, but let's just leave it like that. So I'm going to cancel that 10 with that 20, divide 10 there, divide 10 there. The 9 and the 6 I can divide by 3, so that becomes 3 and 2. So we've now got 3 on the top and 4 on the bottom. Okay, example 4. In a community, the probability of having blue eyes is 0.18. So the probability of blue, 0.18. The probability of having blue eyes and being ambidextrous is 0.04. So blue eyes and ambidextrous, 0.04. Given that 2 out of every 9 people in the community are ambidextrous, so the probability of ambidextrous is 2 on 9. Are being blue-eyed and being ambidextrous independent events? Well, let's find out. So the probability of being ambidextrous, given that you have blue eyes, is the probability of the intersection divided by the probability of blue. It doesn't matter that I've written the letters the other way around, which equals 0.04 over 0.18. And if I simplify that, that is 2 on 9. So yes, that does just equal probability of A. They are independent events. So remember, if their probability is, if the events are independent, probability of A times probability of B over P of B equals P of A. Okay, this is the last example. In another community, all blue-eyed or, so the union, ambidextrous people make up 60%, and I've written that here as 0.6. 60% of the population. Also, the probability of blue eyes is 2/5, and the probability of being ambidextrous is 3/10. Are these independent events? Now, there's a few ways you can work this out. You can do it purely algebraically, or you can do it using a Venn diagram, which I've prepared here. Now, to do a Venn diagram, you just want to decide on a total number of people in the population. Now, 0.6 is the same as 6/10. We can write that as 4/10. We could easily make the total 10 people, or you can make it 100 people if you want to, if that's easier. So you're looking at percentages and use that for your Venn diagram. So the Venn diagram, ambidextrous and blue-eyed. So the union is 0.6, 60%. So if we're going out of 10, that means that there are 4 people that are not in the union. Okay, they're on the outside here, and in all of here, there are 6 total. So probability of A is 3 of 10. So there are 3 total in the A circle. and 4 out of 10 for B, so there are 4 total in the B circle. So this overlap must be 1 person in the middle. So 3 total there, so that's 2 to make 3, and this is 3 there. 1 plus 2 plus 3 is 6. So this is our Venn diagram. So from that, we can say the probability of A given B is 1 out of 4. Does that equal just the probability of A? No, it doesn't. So they're not independent events. Let's also look at the probability of B given A. So B given A is this circle. It's 1 out of those 3. Does that equal the probability of B? No, it doesn't. So they're definitely not independent events. Now let's also look at how you do it just by an algebraic method. So first of all, this is the union. We need the intersection. Now we know the formula that A union B equals P of A plus P of B minus P of A intersection B. Now what we can do is we can add this over to here, and we can subtract this over there. So that's the same as saying the intersection is equal to P of A plus P of B minus the union. Play around with that algebraically if you need to. So in this case, that's 3 on 10 plus, I'm going to use it all over 10, so I'm going to use the 4 on 10 minus the union, which was 6 on 10. So 3 on 10 plus 4 on 10 is 7 on 10 minus 6 on 10 is 1 on 10. And then the probability of A given B equals the intersection divided by the probability of B, so 4 on 10. Now here's a neat trick. When the denominators are the same, 10 divided by 10 is 1, your denominator is 1, your numerators are 1 divided by 4, which is a quarter, so a quarter over 1. It's nice when denominators are the same. Also, the probability of B given A is the intersection divided by the probability of A. So denominator is the same again, 10 divided by 10 is 1, numerator is 1 divided by 3, which is 1/3. So again, we can see here those are not equal to those things. So therefore, these are not independent events. No.